Okay, so I don't know if I asked you, but how's everyone feeling today? Okay, yesterday we talked about series circuits.
Are you serious?
I'm serious. And the main thing about series circuits is that there's one pathway. So all the charge has to go down the same road. So whatever current you have coming out over here, you have the same current going over here. And then you have the same current going over there. So that's the main characteristic about series circuits, is that the currents are all equal to each other. But today's lesson is on parallel circuits. Don't get paranoid. Parallel circuits are just as fun. So with a parallel circuit, there are multiple ways, multiple paths from the positive to the negative terminals of the EMF. And remember, by EMF I mean like the voltage source, whether it's a generator or a battery. The key thing, there's multiple pathways. So for example, I have a battery, connecting wire, then there's a fork in the road. And some of the coulombs go this way, and some of the coulombs go this way. And then they're reunited. Brought back over that way. Now, in that human circuit that we did, we had a 4-volt battery. I say volt, you say? I say volt, you say? A volt is a joules per coulomb. It's the work per charge. It's not the whole work done. It's the work per charge. Yes? So it's the joules per coulomb. So when we had a 4-volt battery, okay, that meant that the battery handed out 4 joules of energy to each coulomb of charge that went through the battery. Yes? In human circuit terms, that would be 4 blueberries per student that went by. So if I'm a coulomb of charge, as I come around over here, I have 4 joules of electrical potential energy. So I'm going to kind of reenact that play we did yesterday, and or the day before. When was it? Yesterday? Day before? Not a play, I mean a little activity. So if this is the total voltage up here, you know, and this is V1, and this is V2, The main characteristic about a parallel circuit is the total voltage is equal to the voltage across the first resistance is equal to the voltage across the second resistance, dot, 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 depending on however many I have in parallel. Now, if I undid this light bulb right here, I unscrewed it, so that just be like an open little branch, what would the other bulb over here do? It would still be the same. Okay? We would be back right to the simple circuit we did the other day. It would be just as bright, no big deal. So each one is independent of each other. Let's talk current, shall we? Up here you have the total current coming out of the battery. Current is measured in amps. I say amperes, you say? Coulombs per second. Ampere. Ampere. Volt. Power or watt. Joule per second. Work over time, joules per second. Alright, anyway, amperes, coulombs per second. So it's like the rate of charge flow. Here you have all the charge flow going through here. But then when you get in the fork in the road right there, some of the charge is going to go this way, some of the charge is going to go this way. So if the charge going this way, if we call that rate of charge flow I1, and if we call this one going this way I2, what's going to be the deal with those little baby currents, the little branches, compared to the big papa current, the IT? Paulie?
They add up to the total.
Exactly. The total current is going to equal the sum of the little baby currents. Notice, these formulas are just the opposite of what they were for the series circuit. Now the voltages are all equal and the currents add up. This is a more popular circuit. All your household plugs are all wired in parallel so that you could turn one off and the other one's still getting all the all the voltage. Each one acts independently. Now, the last thing we have to talk about is the resistance. And it's kind of bizarre with a parallel circuit. So before we just state the formula here, let me just kind of go back to series circuits yesterday. If I had a circuit that just had one resistance, and let's say that it was a light bulb that had a resistance of 1 ohm, and then I had a second one that had 2 identical light bulbs, each one being 1 ohm, well, the total resistance for that first circuit would be 1 ohm. That's the total opposition. But now, after I added a second resistance, now what's the total resistance? See that? Pardon? Well, now the charge has to go through, and now has to go through this opposition, and then even through more opposition. What was the formula for the series circuit for the total? Yeah. So now the total resistance would be 2 ohms. Yes? And if I had 3 of them in series. One ohm, 1 ohm, 1 ohm. Now what would the total resistance be? My man Tom. 3 ohms. See, I can say my man Tom, but I can't say my woman Sita. That just, that doesn't work. Yeah, exactly. So I probably shouldn't say either. Sorry about that. So it kind of makes sense. Every time you add another one in series, the total resistance goes up. And if these were light bulbs, what would be happening to the brightness every time we add another one? They'd get dimmer and dimmer, yes? That's what happened yesterday. That was series circuit. Now watch what happens today. Again, we start off with 1 light bulb in series. Since that's all we have, the total resistance, 1 ohm. But now we're going to add another one in parallel. And it's natural to think, oh, if you're going to add another resistance, the total resistance is going to go up. Not necessarily here. Watch what happens. If this is 1 ohm and this is 1 ohm, look at the difference. Before, if I was a coulomb of charge, I only had one way to get through. I'm going to have to go through here. That's the only way to get through. It's like a 1-lane highway. Everybody's got to go down that 1 lane. But over here, if I'm a positive coulomb of charge, yes, when I get to this point, now there's 2 ways. It's like a 2-lane highway. I could go this way, or I could go this way. Since there's twice as many ways to get through, guess what's going to happen to the total resistance? Nope. It goes down. It's going to be half. So over here, the total resistance is a 1/2 ohm. Kind of like a wire. If you had a wire, and then you had a wire that was twice as fat. If the wire was twice as fat, what happens to the overall resistance? Decreases, yes? Same thing over here now. It's not a fatter wire, but now there's just more ways to go through. Just like here, there's more ways to go through. So the total resistance goes down. Let me just finish up this scenario, then you can take your break. But what if you had 3 ways to go through? 1, 2, 3. If each of these was 1 ohm, what would be the total resistance now? It's like a 3-lane highway. There's 3 ways to get through. Read? 1/3. So the total resistance would equal 1/3 of an ohm. Take a break, come on back. All right, how's everyone still feeling?
Awesome, sir.
As you can see, each time you add another resistance in parallel, the total resistance goes down. So back to my blueberry human demonstration, if there was 2 ways to go through, it would be easier for the battery to push them through, because now there's more lanes over there. So the battery can actually push them through and hand out the blueberries twice as fast. So if I had 2 light bulbs in parallel now, the battery is going to be handing out 4 at a time. They still hand out 4 at a time because the voltage of the battery didn't change. It's just moving the current twice as fast. And the question is, well, how does the battery know what's out there? Well, as soon as you have the complete loop, there's an invisible electric field that goes through the wires, and the battery can sense, what that force field is. And it's like, oh my God, it's so easy now. And if you hooked up another one, you're like, oh my God, this is really easy. And it would just heat them out faster. So every time you add another one in parallel, you're using more and more energy. Now, this is nice when you have identical resistances, because the total resistance 1 gets cut into half or gets cut into 3/3. But if they're unequal, it's a more complicated hidden relationship. If they're unequal, you have to use this formula. 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus ... That does not simplify down to RT equals R1 plus R2. And you have to be careful, because after you crunch out the left-hand side, you're used to being done, like, oh, I did my work. But not here. After you crunched out the right-hand side, is that your total resistance? What do you still have to do, Dave?
Reciprocate it?
Yeah, you got to take the reciprocal. So, be careful of that. Now, not only do you have these three formulas, 1, 2, 3, for parallel circuits, but you could also use Ohm's law for each of the devices. So, as well as these three, you have VT equals, IT times RT, and V1 equals I1 times R1, and V2, whoa, what happened there? And V2 equals I2 times R2. So those formulas hold as well. So let's try a practice problem. So let's see, we have a 120 volt potential difference. So our EMF is 120 volts. We have two resistances in parallel, and what we want to calculate is the total current coming out of the battery the current going through this resistance, the current going through this resistance, we want to calculate the amount of energy used across that first resistance per coulomb, and the energy used going across that bottom one per coulomb. And finally, we can also calculate the total resistance of the circuit. So since it's a parallel circuit, what's the main characteristic that's the same in each branch? You think parallel circuit, you should think of that factor first. Say it loud, say it proud, Mr. Weberman.
All the voltages are 120
Yeah, exactly. So since the total voltage is going to equal, the first voltage is going to equal the second voltage, if there's a 120 voltage handout up top, then we know the voltage right here is going to be 120 volts, and the voltage down here is going to be 120 volts. And then the next thing I recognize is for the lower two branches, I have 2 out of the 3. I recognize right there I have 2 out of the 3, and here I have 2 out of the 3. And anytime you have 2 out of 3, how do you get the third? Brrr. Oopsie. Now, does that make sense? There's going to be 6 amps going through the bottom resistance and 12 amps going through the top one? Why does that make sense, Swati? Why is there more current going that way and less current going down through the bottom one? The answer lies with the resistances. What's the deal with that lower resistance? It's higher, so it's harder to get through that way. So that's why less current goes that way, because it's harder to get through there. Here it's easier to get through there, so more go that way. And then once we know the 2 little baby currents, what do we figure out next? Rosie? We can figure that out. We totally can figure that out. But what if I wanted to figure out the total current? Now that I know the 2 baby currents, right, I could find the total current. We got 12 amps and 6 amps. That's it. Thank you. That's the total current. Total current here. Somebody asked with those defibrillators how much current, goes through the person's heart when they shock them. It was in one of the homework problems, or one of the questions is it was 18 amps. Of course, it's just for a millisecond, because remember we read 0.07 amps for a second long would be enough to kill a person. But to give them a little jolt to get the heart back to its right rhythm, 18 amps. Anyway, last but not least, we can calculate the total resistance, as Dorothy was saying, and there's actually 2 different ways of calculating it. Let's first look at the easier way. Because we have 2 out of the 3, so VT equals IT times RT. we have 120 volts. IT is 18 amps. So what's the total resistance? 120 divided by 18. That's going to be 60 divided by 9. It's going to be what? So about 6.6 ohms. Again, it's always kind of bizarre because how does the total resistance compare to the individual resistances? How does the total compare to the individual resistances, Claire? Exactly. How bizarre. Dun, 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 dun. How bizarre. How bizarre. Dun, dun, dun. The total resistance is less. The other way of getting that total resistance is using the 1 over R formula. So why don't you take a moment now to make sure you can crunch it out that way. I myself, I like to use the x to the negative 1 button. You guys familiar with that button? That's funny. So I would put in like 10 and hit the 1 over x button. Plus 20, 1 over x. Equals 1 over x button. Did you follow me on that, people? And then I'd hit my, x to the negative 1 button. And then plus 20, and I hit that x to the negative 1 button. And then I hit, enter or equals. And then when I'm done with that, I have to hit my x to the negative 1 button again. 1, 0, x to the negative 1, plus 2, 0, x to the negative 1, enter, x to the negative 1. Does it work out? Do you get like 6.6? Yeah. So, in summary, parallel circuit. What's one thing we learned about today about parallel circuits? Yo, say it loud, say it proud. Put your hands in the air. Give me a stare. Come on, come on.
Come on, come on.
What's that? Voltages are the same. Mr. Fox, what's another thing we learned about parallel circuits?
Total resistance is less than individual resistance.
Exactly. It follows that weird formula. 1 over RT equals 1 over R1 plus 1 over R2 plus however many you have. And finally, what's the deal with the currents there, Jacob? How does the total current compare to the little baby currents? Think of a river, and then the river breaks up into little forks. The little ones add up to the total. Total current equals the sum of the the baby currents.